if you were in my MATSE 112 class. Polyphenylene oxide also has that big benzene ring. It's polarizable, and so these form miscible blends. Polyethylene terephthalate and polybutylene terephthalate also form miscible blends. They're just variations on a theme, so you can look up those chemical structures. And also polymethyl methacrylate, which is a polar polymer, right? It's got that acrylate group hanging off the side, which looks like an ester. That's polar. And you know the chemical structure of PVDF, or PVDF is a polar polymer because it has CH2, CF2. So both of these polymers contain dipoles, and if they're both polar, they tend to form what? Miscible blends, right? They're miscible with one another because they have specific interactions between the dipoles in the polymer. If you want more information, this is a really nice polymer educational site, and it's free to check out, so I suggest you take a look at it. You can do basically 50% of your curriculum just by understanding macrogalleria. Okay, miscible polymer blends. Make sure you know these examples as, you know, if someone walks up to you at a party or on the street and say, hey, what's a miscible polymer blend? You got it. Any questions? Believe me, it happens. All right, if it's not miscible, it's immiscible or heterogeneous. Those are the same thing. And so polystyrene and polybutadiene look different, right? There's no aromatic ring in polybutadiene. You know, there's no reason why these should mix. And so one's not polar and the other nonpolar. They're both nonpolar, right? Or mostly nonpolar. But because there's no aromatic ring here, there's no reason that polybutadiene will want to mix with polystyrene. And so if you try and blend these two polymers, what happens is you'll get one phase of polybutadiene and you'll get another phase of polystyrene. What's the volume fraction or the area fraction in this picture? How much polystyrene is there and how much butadiene is there? Ballpark. What's your engineering sense tell you? 80-20, 85-15, 90-10, you know, whatever you want, 75-25. But it's majority polystyrene, right? And minority polybutadiene. And notice the polybutadiene does not connect. So the minority phase is segregated into what we might call domains, and we have a continuous phase of polystyrene. What are the mechanical properties of polystyrene? Does anyone know? It's brittle, right? It's a hard piece of plastic, right? It's a cheap champagne wedding cups, right? So what do you think this material is? What's the modulus? Let's start with the modulus. What's the modulus of this material? Right here. Probably close to what? What do you think? If you squeeze this thing, what are you going to feel? Polystyrene, right? Polystyrene's a continuous phase. That's what's connecting one side of the material to the other. So the modulus of this thing is going to be more like polystyrene and less like polybutadiene. This gentleman in the front here said that polystyrene is brittle, and that's exactly right. It turns out if you put a little bit of polybutadiene in there, you get high impact polystyrene, which means you get polystyrene that's not brittle anymore. You get polystyrene that's tough. And tough is a scientific word. It means the area under the stress strain curve. You'll learn that, or you know that from your mechanical properties class. So high impact polystyrene, or HIPS, is not a perfect example of a miscible polymer blend because it's actually a graft copolymer. And so you make polybutadiene and you graft polystyrene through that. You'll learn how to make high impact polystyrene in Professor Chung's MATSE 441 class if you take polymers from him. But it still shows this really interesting morphology. And this is just a cartoon, but if you crack open a piece of high impact polystyrene, you'll see exactly the same thing under the SEM or TEM. You'll see little domains of polybutadiene in polystyrene. And that totally changes the mechanical properties, it totally changes the application space, and it makes polystyrene a better material than just for champagne cups at weddings. Okay, that's all covered. But this is an immiscible blend now, and I don't show you a picture of a miscible blend because what do you think the picture would look like? In a miscible blend, what would this look like? If polystyrene and polybutadiene were miscible, let's just pretend, what would this picture look like? Green. Yellow and blue make green, right? You have mixing at the molecular level in a miscible blend. In an immiscible blend, even if you add 1 or 2% of polybutadiene, it will not interact with the polystyrene chain, so it has to find its own place. Any questions so far? All right. Here's polymer miscibility table right here. You notice it looks like the solvent miscibility table. And so if we take PET and we run along here to this thing, that might be PET there because the diagonal is blacked out. But anyway, this denotes compatibility. So ABS is miscible with acrylic. So you should know what acrylonitrile butadiene styrene is. You use it in 3D printing. You make Legos out of ABS. It's a really important polymer. And does anyone know what the scientific or the chemical name for acrylic is? Polymethyl methacrylate, right? So it's an acrylic type of polymer because it has an acrylate in it. But anyway, you can take ABS and you can mix it with acrylic and you form a miscible blend or a compatible blend. And then, let's see, the circles, compatibility in some cases, whatever that means, because there's exceptions. And then you notice most of these squares are what? Open, which tells you what? Most polymers don't like to mix. And that's a really interesting factoid. So we all know it's important to recycle polymers. We want to save the earth. Why do all polymer bottles have a little number on the bottom? Polymers don't like to mix, right? We want to recycle similar polymers with similar things. It turns out if you take all that recycled plastic, 1, 2, 5, 6, whatever it is, put it all together, you get a big piece of junk. And you make a park bench out of it, or you make that engineered lumber out of all that jumble of polymers, because you can't make anything good out of a polymer blend unless you're lucky enough to hit one of these compositions. And so the entropy of mixing is very low for polymers, and so they usually don't like to mix. And we'll get to that in a sec, because you know I like to talk about entropy. Question in the back.
If they were all different polymers were mixed, so is it very difficult to like extract individual ones? Like, does it actually just become a heap of like indescribable polymer?
So how do they separate plastic? So like in State College, if you live in the borough, you can throw all the plastics in one bin, and they have to separate it. So I don't have any different numbers at my house. I just throw all the plastics together. How do they separate it at the landfill? In water, they use a density column. So not water, but they have a column with different densities created by different salt solutions, and the plastic will float up to different densities, and that's how they separate it, because polymers all have different densities. Yeah. So they tend to separate polymers not by melting them, but by putting them in solution and grind them up and separate them that way. Good question. Any other questions? Okay. So the one thing that we should mention, and this is a really important part of polymer technology, is this issue of compatibilizers. So if you have an immiscible blend that looks like this, and you add a compatibilizer, you notice now we have this yellow shell around this orange thing, and this yellow shell is called a compatibilizer, or a bridge between one phase and the other phase. Does everyone know what a surfactant is? Good. What does the surfactant compatibilize? Where do you use surfactants? At the surface, yeah, polar and nonpolar, right? So if you have oil and water and you add a surfactant, that's why you put mustard in your salad dressing or mayonnaise or something else. So you have oil and water salad dressing and you put a little something else in there. That's a surfactant, and that brings those phases together when you make a nice vinaigrette, right? And so this compatibilizer is the little something that ties together these two different polymer phases and allows them to more easily mix, or to make smaller phases, or to make it more homogeneous. Of course, we're never going to get to the point where orange is going to go into blue because at the molecular level, these are immiscible polymers, but the compatibilizer helps us. So think about the salad dressing example. Block copolymers, if you studied them or you know what they are, can act as compatibilizers. And so if you have an immiscible blend and you make a block copolymer, the green block likes the green. The red block in this case likes the yellow. You can use this block copolymer as a compatibilizer, or a block copolymer surfactant is also a thing. You can use this to tie together the phases. So if you're interested in compatibilizing two different polymers, sometimes people make block copolymers out of those two things. The block copolymers are really expensive, so you just want to use 1 or 2% of them because there's only 1 or 2% of this surface, takes up the volume, and then you use the cheap stuff to make up the bulk of the material. Okay. Last thing about polymer technology, and then I'm going to show you some equations to wake you up at the end, and it'll get exciting after this. Compatibilizers are also used in composites. So who here is interested in Formula One racing cars, or airplanes, or golf clubs, or tennis rackets, or any of that stuff? I am. I like them all. Those are all composites, right? Carbon fiber composites, or glass composites, or Kevlar composites, but all composites have chemistry or a compatibilizer at the interface between your carbon fiber. So a neat carbon fiber is just pure. Pure is the scientific term for neat. And then your resin is the polymer, so that's the epoxy that you put in your carbon fiber composite, or that's the plastic that you put in the fiberglass. If anyone's here ever made a canoe or something like that and you do all the nasty fiberglassing, these glass fibers or these carbon fibers have a compatibilizer on the surface that connects the fiber to the resin. And this is the only reason why the Dreamliner works the way it does. If we didn't have coupling agents, we could never have high-performance carbon composites because you can't get the carbon fiber to stick to the resin. You need the carbon fiber for strength, you need the resin for ductility and all the good stuff about polymers, but the Dreamliner would never work if we didn't have these compatibilizers, and they're also called sizing agents. So when you go work for Arkema or you go work for DuPont or Dow, people will say, you're going to be in the sizing division. And you say, well, I don't know what that is, but you're going to treat all these fibers and then sell them to the people who make composites. Okay, what time does this class end? Oh, we got tons of time. This is great. All right, get ready for math. I suggest you write some of this stuff down because you're going to need it. And I will post the notes again. All right. So we're going to talk about entropy. And who here had me for MATSE 112? Great. You guys know all this stuff. It's easy. You can get your old notes. It's going to be good. All right. So we have two liquids, right? Liquid A and liquid B. They're separate. They're pure. They're in their own thing. We remove the barrier and they mix. What has happened to the entropy between here and here? Increase, right? So that's the driving force in some cases for mixing, is that the entropy increases. And we know that the universe likes to increase entropy. And so if we have an increase in entropy, those processes can be thermodynamically favorable. But we have to think about delta H as well, which we will sooner or later. But in general,